They were told American science was primitive, built on borrowed European genius and lucky accidents. But when the heavy steel door swung open on that cold morning in May 1945, 3 German physicists stood frozen in the doorway of MIT's radiation laboratory, and one of them began to weep. What they thought would give them hope instead shattered everything they believed about their own superiority. The spring air in Cambridge carried the scent of fresh-cut grass and motor oil, but inside that massive building, the smell was different. It was the sharp bite of solder and electrical insulation, the clean scent of new machinery, the faint ozone tang of high-voltage equipment running constantly. Dr. Werner Heisenberg had prepared himself for this moment during the long flight across the Atlantic, rehearsing in his mind what he would say, how he would maintain his composure, how he would observe everything with the cool detachment of a scientist. He had survived the collapse of the Third Reich, survived the questioning by American intelligence officers, survived the humiliation of being held in a British country house while the world learned about Hiroshima. He thought he had survived the worst of it. But he was not prepared for this. The American officer escorting them was young, perhaps 25, with an easy smile and a casual manner that still unnerved German scientists accustomed to rigid military formality. He wore his uniform jacket unbuttoned at the collar, and he chewed gum while he walked, making small talk about the weather and asking if they wanted coffee. Real coffee, he said, not the ersatz chicory mixture that had sustained Germany through years of blockade. The scientists followed him through corridors that seemed to stretch forever, past door after door with small windows revealing laboratories filled with equipment. So much equipment. Equipment that gleamed under bright fluorescent lights. Equipment that hummed with electrical life. Equipment that bore the stamps and labels of a dozen different American manufacturers. Their minds could not reconcile what they were seeing with what they had been taught. German engineering was the finest in the world, they had been told. German precision, German innovation, German scientific discipline had no equal. The Americans were shopkeepers and farmers, good at mass production perhaps, but lacking the theoretical depth and technical sophistication that came from centuries of European academic tradition. This is what they had believed, what their colleagues had believed, what their government had told them throughout the war. But here, in this building in Massachusetts, that belief crumbled with each step down the corridor. The officer stopped at a door marked "Microwave Research, Authorized Personnel Only," and produced a key. He turned to them with that same casual smile and said something that would echo in their memories for decades. "This is just one of our labs," he said. "We have 17 buildings like this one." Then he opened the door. The room beyond was not large, perhaps 30 feet by 40, but every surface was covered with instruments. Oscilloscopes with screens larger than any they had seen in Germany. Signal generators with frequency ranges that should not have been possible with existing tube technology. Waveguides machined to tolerances that would have required weeks of work in the best German shops. Yet here they were stacked on shelves like common pipe fittings. And in the center of it all, mounted on a sturdy steel table, sat a magnetron. Dr. Ernst Bruch moved closer to the magnetron, his hands trembling slightly. He had worked on microwave technology in Berlin, had struggled for months to achieve stable output at centimeter wavelengths, had written papers about the theoretical limits of cavity magnetron design. The device before him was smaller than anything his team had built, yet the specifications written on the tag attached to its base indicated it produced more than 10 times the power output. More than 10 times. He reached out to touch it, then pulled his hand back, uncertain if he had permission, uncertain if he could trust his own eyes. The American officer noticed the gesture and laughed, not unkindly. "Go ahead," he said. "We have hundreds of them, thousands actually. Raytheon's manufacturing plant in Waltham turns out about 2,600 of these per day." Per day. The words hung in the air like a physical weight. Bruch's team in Berlin had produced 6 cavity magnetrons in 4 months, and each one had been treated like a precious artifact, handled with extraordinary care, celebrated as a triumph of German engineering. The Americans were making thousands of them each day, not each month, Not each week, each day. It was not the technology itself that broke them in that moment, but the scale, the impossible, incomprehensible scale of American research and production. Dr. Hans Kummerow had remained silent until now. Standing near the doorway, his arms crossed over his chest in a posture that might have been defiance, or might have been an attempt to hold himself together. He was older than the others, nearly 60, with gray hair and deep lines around his eyes from years of squinting at laboratory instruments under inadequate lighting. He had taught physics at the University of Göttingen before the war, had trained some of Germany's best young scientists, had believed absolutely in the superiority of the German educational system. American universities were diploma mills, he had told his students. They valued athletics over academics, permitted women and Jews into their programs, lacked the rigor and discipline that produced true scientific minds. But now he was looking at the results of that supposedly inferior system, and his certainty was evaporating like morning dew under a harsh Sunday. The American officer was still talking, explaining the magnetron's development history with the enthusiastic tone of someone discussing a favorite hobby. The British had invented the basic design, he said, and brought it to America in 1,940 inches, a desperate attempt to develop better radar. MIT had taken the prototype and improved it, then worked with American manufacturers to scale up production. The engineering guys figured out how to make them fast and cheap, he explained. They treated it like any other manufacturing problem. Assembly lines, interchangeable parts, quality control processes. Nothing fancy, really. Just good industrial practice. Nothing fancy. The casual dismissal of an achievement that would have been celebrated as a national triumph in Germany, reduced to nothing fancy by a young American officer who probably had a bachelor's degree from some state university. Heisenberg finally found his voice. "How many scientists worked on this project?" he asked in careful English. The officer thought for a moment. "Here at the Rad Lab, I think we had about 4,000 people at peak. But a lot of them were engineers and technicians, not scientists. We pulled in physics professors from all over the country, gave them security clearances, set them up with whatever equipment they needed." He gestured around the room. Most of them had never worked on military projects before. They were teaching undergraduates a few years ago. Now, they're designing fire control systems for battleships. 4,000 people, in one laboratory, at one university, working on one aspect of one technology. The scale kept expanding, like a balloon inflating beyond any reasonable limit, and the German scientists felt themselves shrinking in response. Heisenberg had led Germany's uranium project, the great hope for atomic weapons that would turn the tide of war. His team had numbered perhaps 100 scientists and technicians at its largest, spread across several cities, constantly short of materials, competing with other military projects for resources and personnel. He had thought that was normal. He had thought everyone was working under similar constraints. But the Americans had not been constrained. They had not been forced to choose between projects or ration resources or make do with inadequate equipment. They had simply decided what they needed and built it, on a scale that defied comprehension. The tour continued through the building, each room revealing new wonders and new humiliations. A laboratory filled with radar displays, each screen showing crisp, clear images of aircraft tracked at distances that German radar could never achieve. A workshop where machinists were fabricating components with casual precision, tossing aside pieces that did not meet specifications, starting over without apparent concern for wasted material. A storage room stacked floor to ceiling with vacuum tubes of every conceivable type, enough to outfit 100 laboratories. And everywhere, that same abundance, that same casual assumption that there would always be more. More materials, more equipment, more trained personnel, more time, more space, more everything. They passed a break room where several young men in shirt sleeves were drinking coffee and arguing cheerfully about some technical problem. One of them had his feet up on a desk. Another was throwing a small rubber ball against the wall while he talked. They looked like students, barely old enough to shave, but the equations scribbled on the chalkboard behind them were sophisticated analyses of waveguide propagation. Graduate students, the American officer explained. MIT had dozens of them working on the radar project. Bright kids, he said. Really bright. They figured out problems that had stumped the senior guys. Brüche thought of his own graduate students in Berlin, most of them conscripted into military service by 1943, sent to the Eastern Front or put to work in factories. The waste of it struck him with fresh force. All that training, all that potential, thrown away because the Reich needed infantry replacements or factory workers. Meanwhile, America had kept its young scientists in laboratories, given them problems to solve, allowed them to do what they had been trained to do. Which system was truly superior? The question formed in his mind, unbidden, unwelcome, undeniable. The tour ended in a conference room where large photographs covered one wall, showing various radar installations in the field, ship-mounted radar systems, aircraft-mounted radar systems, mobile ground units, coastal defense stations. Each photograph was labeled with technical specifications that would have seemed like science fiction a few years earlier. Detection ranges of over 100 miles, automatic tracking of multiple targets, integration with fire control computers that could calculate firing solutions faster than any human crew. The American officer invited them to sit, and someone brought coffee in thick ceramic mugs. The coffee was strong and hot and real, and Heisenberg wrapped his hands around the mug, grateful for something solid to hold. He felt untethered, adrift in a reality that did not match the map he had been carrying in his mind. "I want to understand," he said carefully, choosing his words with precision. "How did you organize this? How did you bring together so many people, so many resources, so quickly?" The officer shrugged. The National Defense Research Committee coordinated most of it. They identified what the military needed, then found the right people to work on it. Universities, private companies, government labs, everyone just kind of pitched in. He paused, seeming to search for words to explain something he considered obvious. When Pearl Harbor happened, everyone wanted to help, the government asked, and people showed up. Scientists, engineers, factory workers, we all knew what was at stake. Everyone just kind of pitched in. As if assembling the most sophisticated research establishment in the world was a neighborhood barn raising, something neighbors did for each other without much fuss. But beneath the casual words, Heisenberg heard something else. He heard a fundamental difference in how American society functioned, how it mobilized talent and resources, how it turned individual capability into collective achievement. The German system had been built on hierarchy and control, with decisions flowing down from above, with scientists doing what they were ordered to do by military authorities who often did not understand the technical issues. The American system seemed almost chaotic in comparison, yet it had produced results that the German system could not match. Kummerow spoke up, his English more heavily accented than Heisenberg's. And funding? Who decided how to allocate funds? Congress appropriated the money, and the NDRC distributed it based on what they thought would work. The officer smiled. They made some wrong bets, backed some projects that went nowhere. But they backed enough different approaches that something usually worked out. They made wrong bets. They had the luxury of failure, the freedom to waste resources on projects that went nowhere, because there were always more resources available. Germany had been forced to guess right the first time, every time, because there was no margin for error, no second chances. The weight of it settled over the German scientists like a heavy blanket. They had not lost the war because of some crucial mistake or some failure of will. They had lost because they had been competing against a nation with 10 times their industrial capacity, 100 times their material resources, and a social system that could mobilize talent with an efficiency that German planners had never imagined. That night, in the hotel where American intelligence had housed them, the three scientists sat in Heisenberg's room and spoke in quiet German, certain their conversation was being monitored, but too exhausted to care. Brüche sat on the edge of the bed, his head in his hands. Kummerow stood by the window, looking out at the lights of Cambridge, at the cars moving through streets that showed no sign of bombing damage, at the bright shop windows and the people walking without fear through the evening darkness. "We were children," Bruche said finally, "playing with toys while the adults worked next door." Heisenberg wanted to argue, wanted to defend their work, wanted to point out that German science had made genuine contributions, that they had worked with dedication and skill under difficult conditions. But the words would not come. He had seen too much that day. The evidence was overwhelming. "They had everything," Kummerow said, his voice flat, "and we had nothing. That is the truth of it." But it was not quite the truth, Heisenberg thought. Germany had not had nothing. Germany had talented scientists, skilled engineers, good universities, strong industrial traditions. What Germany had lacked was something more fundamental. It had lacked the social trust that allowed collaboration across institutions. It had lacked the economic depth that allowed failure without catastrophe. It had lacked the political system that could harness free minds rather than trying to control them. Most of all, it had lacked humility. German science had believed itself supreme, had dismissed American achievements as lucky accidents or stolen ideas, had refused to learn from others because learning implied inferiority. That arrogance had been more crippling than any material shortage. The tears that had come earlier, standing in that laboratory surrounded by American abundance, had not been tears of envy or frustration. They had been tears of recognition, of understanding, of seeing clearly for the first time how profoundly wrong they had been about everything. The following days brought more tours, more revelations, more quiet destructions of long-held certainties. They visited the radiation chemistry laboratories where researchers were studying the effects of intense radioactivity on materials, work that implied access to radiation sources far more powerful than anything available in Germany. They saw the computer laboratory where massive calculating machines were solving differential equations, each machine filling an entire room but processing mathematics faster than teams of human computers with mechanical calculators. They toured the electronics workshops where technicians were assembling proximity fuses for artillery shells, a technology so sophisticated that German intelligence had assumed it must be impossible to produce in battlefield quantities. But it was the people more than the equipment that continued to surprise them. The researchers they met were skilled and knowledgeable, but they were not the rigid, formal scientists of German imagination. They were friendly and casual, working in shirt sleeves, calling each other by first names regardless of rank or seniority. They seemed to argue constantly, debating technical points with a freedom that would have been considered disrespectful in a German laboratory. Yet somehow these arguments led to better solutions. A young woman physicist explained her work on signal processing, and the German scientists tried not to show their shock at finding a woman doing serious research. She had graduated from Berkeley, she told them, and came to MIT specifically to work on the radar project. Her equations on the chalkboard were elegant and correct, and she answered their technical questions with confidence and precision. In Germany, she would have been barred from most university programs, dismissed as unsuited for serious scientific work. Here, she was simply another member of the team. They met a Japanese-American researcher whose family had been held in an internment camp while he worked at Los Alamos on the atomic bomb project. The contradiction was stark and troubling. America had imprisoned people based on ancestry, a policy that echoed Germany's own racial laws, yet had also recognized talent and ability across racial lines in ways Germany never had. The American system was not perfect, not by any measure, but it was flexible enough to make use of capable people even when prejudice said they should be excluded. These contradictions multiplied with each encounter. America was deeply flawed in ways that German propaganda had correctly identified: racist, materialistic, often crude and anti-intellectual in its popular culture. But it was also dynamic and open in ways that allowed it to harness human potential with remarkable efficiency. It wasted resources on a scale that would have scandalized German planners, yet its abundance meant that waste did not matter. It was chaotic and disorganized compared to German systematic planning, yet the chaos somehow produced better results. On their fourth day in Cambridge, they were taken to see the Van de Graaff generator at MIT's high-voltage research laboratory, The massive machine could produce electrical potentials of several million volts, generating artificial lightning in a controlled environment. The physicist demonstrating the generator was enthusiastic and talkative, explaining how they used it to study electrical breakdown in insulators, to test components for high-altitude aircraft, to investigate the fundamental physics of electrical discharge. "We built a bigger one down in Tennessee," he mentioned casually. For the Manhattan Project, needed higher voltages for some of the isotope separation work. The Manhattan Project, the American atomic bomb program. The scientists had heard about it, of course. Everyone in the world had heard about it after Hiroshima. But hearing this physicist mention it so casually, as just another research project among many, drove home the scale of American scientific mobilization in a new way. Heisenberg gathered his courage and asked the question that had been haunting him. How many people worked on the Manhattan Project? The physicist thought for a moment. At the peak, maybe 130,000 people. Most of them were construction workers and operators at the production facilities. But there were several thousand scientists and engineers. Los Alamos alone had a couple thousand people. 130,000 people. The entire German uranium project had never employed more than a few hundred. Heisenberg felt the familiar sensation of the ground shifting beneath his feet, the constant recalibration of understanding that had marked every day since arriving in America. "And the cost?" he asked, though he was not sure he wanted to know the answer. "I heard it was around $2 billion, maybe more." The physicist said it without particular emphasis, as if mentioning the price of groceries. $2 billion. The figure was abstract, almost meaningless in its enormity. Germany's entire uranium project had struggled for funding, had competed with other weapons programs for limited resources, had been forced to make do with inadequate facilities and equipment. The Americans had simply decided to build atomic bombs, and had thrown resources at the problem until it was solved. It was not about genius or superior science. It was about will and capacity, about deciding that something must be done, and then doing it regardless of cost. That evening, Heisenberg wrote a letter to his wife back in Germany. The American censors would read it before it was sent, but he did not care. He needed to put his thoughts into words, needed to make sense of what he was experiencing. "We thought we were at the forefront of science," he wrote. "We thought our methods were superior, our training more rigorous, our understanding deeper. But we were looking at the world through a very small window, seeing only what confirmed what we already believed. The Americans have shown me a larger view, and I am humbled by it. Not destroyed, not broken, but humbled in a way that might, eventually, be healthy for us all." The tears had dried, but the understanding remained. The American research facilities were impressive, not because they were filled with geniuses or built with stolen secrets. They were impressive because they represented a different way of organizing human effort, a different set of assumptions about what was possible, a different relationship between individual talent and collective purpose. The German scientists had been taught that progress came from hierarchy and discipline, from great minds working in isolation, from careful control and systematic planning, but the American facilities showed a different model. Progress came from collaboration and argument, from diverse perspectives and free exchange of ideas, from abundance that allowed experimentation and failure, from trust that allowed talented people to work without constant supervision. It was a lesson that went far beyond science and technology. It was a lesson about societies and systems, about what happens when you try to control everything versus what happens when you create conditions for people to contribute freely. In the final days of their visit, the German scientists were taken to the factory floor at Raytheon, where those thousands of magnetrons were produced each day. The assembly line stretched the length of a massive building, with workers at each station performing specific tasks with practiced efficiency. Components arrived at one end, finished magnetrons emerged at the other, and the whole process moved with mechanical rhythm. But what struck the scientists was not the machinery but the workers. They were mostly women, wearing work clothes and protective glasses, their hands moving with quick precision as they assembled delicate components. In Germany, Such workers would have been considered unskilled labor, suitable only for the simplest tasks. Here, they were building sophisticated microwave devices that required genuine understanding and attention to detail. One of the American engineers noticed the scientists watching and came over to talk. "We trained them all," he said with evident pride. "Took about 6 weeks to bring someone from no experience to full productivity. They're good workers, better than some of the men, honestly, more patient with the detailed work." The casual meritocracy of it was striking. American industry used whoever could do the job well, regardless of gender or background. German industry had clung to traditional hierarchies even when those hierarchies limited productivity. Another small difference, another small advantage, multiplied across millions of workers in thousands of factories. The German scientists flew back to Germany in late June, their heads full of images and numbers, their hearts heavy with understanding. They had seen the future, and it was not German. The future belonged to systems that could mobilize talent widely, that could waste resources productively, that could trust people to do important work without rigid control. Some of their colleagues, hearing about the American facilities, refused to believe the reports. The numbers must be exaggerated, they said. The Americans must be lying, showing off mock-ups and prototypes while hiding their real limitations. It was easier to believe in deception than to accept the truth. But those who had seen knew better. The tears had been real. The shock had been real. The revelation had been real. In the years that followed, as Germany rebuilt from the ashes of total defeat, some of those lessons were absorbed and applied. German science became more collaborative, more open to international exchange, more willing to learn from others. The rigid hierarchies softened. The arrogance faded. In its place came a more humble recognition that good ideas could come from anywhere, that progress required freedom as much as discipline, that abundance was not just about material wealth, but about abundance of opportunity and trust. The magnetrons kept running in American laboratories, churning out microwaves, pushing the boundaries of what was possible. But they had already served a deeper purpose. They had been mirrors, reflecting back to German scientists an image of themselves they had never seen clearly before. Not just defeated enemies, but people who had believed their own propaganda, who had mistaken style for substance, who had confused rigid control for true strength. It was not the last time that experts would be surprised by American capacity, not the last time that careful observers would underestimate a system that appeared chaotic and inefficient. The lesson would need to be learned again and again by different people in different contexts, because the truth contradicted so many comfortable assumptions about how progress happens and who makes it. But for those German scientists standing in that laboratory in Cambridge in the spring of 1945, watching steam rise from their coffee cups while they stared at racks of instruments they could not have built in a dozen years, the lesson was immediate and visceral and complete. They had been taught that they were the best, but they had just learned what best really meant, and the knowledge broke something in them that needed to be broken. In the breaking came the possibility of rebuilding, of understanding, of becoming something better than what they had been. The American officer had said it without irony or boasting, just stating a simple fact: this is just one of our labs. One laboratory, among dozens, among hundreds, in a nation that had decided to win a war and had simply made it happen through the application of organized capability on a scale that defied imagination. That was the truth that brought tears. Not envy but recognition. Not shame but understanding. Not defeat but the hard, necessary beginning of wisdom. And there remain thousands more stories like this, waiting to be remembered and understood by anyone willing to look clearly at what actually happened, rather than what we were told happened.